Okay. So welcome to week 9 of the MA106 Category Theory course. I am Shubhajit. I am a PhD student at the Department of Mathematics at IISc. And as we keep doing, we'll solve problems from week 9. So a brief summary of whatever you saw this week. Okay, so in this week, you saw the definition, or rather the notion of a monoidal category, which is exactly the data of a category together with a bifunctor from C cross C to C, an object I, a natural isomorphism alpha, a natural isomorphism lambda, and a natural isomorphism rho, which are given in this way. So before that, let me ask you, what is a do you know what a bifunctor is? Okay. Yeah. So it's exactly just a functor whose domain category is a product category. That's all. So I is an object in C called the unit object. Alpha is a natural isomorphism. So alpha is the associator. It's a natural isomorphism from what to what? Yeah, so it's supposed to capture associativity. So it should be a natural isomorphism from what to what? Alpha is a natural isomorphism oh, yeah, in a sense, yeah. Alpha is a natural isomorphism with components from x tensored y tensored z to x tensored y tensored z. Each has to be an isomorphism for alpha to, each component has to be an isomorphism for alpha to be a natural isomorphism. So this is a natural isomorphism of trifunctors, so to say. One of them is this functor. Okay, let's write it in this way. Oops. Yeah. Which is a functor from C cross C cross C to C, doing the obvious thing as the notation suggests, and you also have the other functor. So it's a natural isomorphism. Lambda is a natural isomorphism from what to what? I mean, with component. Okay, so this might be a bit, this is not a well posed question in the sense. So let me just write it with components lambda x from 1 tensored x to x, and rho is a natural isomorphism with components rho x from x tensored 1 to x. We must have these things here. So the idea is that usually we would expect one to behave like a unit object or an identity object for some operation. But since we are talking about categories, we know that equalities are not the right kind of, I mean, not the right way to compare two things or say that two things are same. So the healthier notion rather is the notion of an isomorphism, which is exactly what we want here. Okay. Yeah, so this is the idea or the notion of a monadal category, and this is subject to subject to what? Okay, subject to the commutativity of some type. Yeah. Certain diagrams. So why is it called a coherence axiom? Pentagon axiom, or the pentagon diagram, and the triangle axiom, which I won't write right now. Yeah. So it's called a coherent diagram because it exactly sort of is the necessary thing that you need. So what do this alpha, lambda and rho do? They identify one parenthesized product with another parenthesized product, right? That is what they do. Now what you would want is, using this alpha, lambda and rhos, you can basically, suppose you are given two parenthesized products of objects, same objects in the same order. What you would want is, what you could have is, you could have two different isomorphisms. You can build two different isomorphisms out of them. What those coherence diagrams or commutativity of those coherence diagrams assures you is that any two such identifications will be equal. So in a sense, this is something very natural to expect here, because what you want is, you should have a common identification for bracketings, okay? So that you don't run into ambiguities or issues. Yeah, so this is the data of a monadal category. And what are some examples of monadal category? One example or some examples? Okay, so let's write it like this: AB tensored over Z with Z. Then set with product structure. Yeah. No, so basically, if you look at some authors also sometimes write it like a box. Okay, so the idea was essentially to obtain a notion using tensor. To make an abstraction of the notion of tensor. Certainly, this tensor that we write for a monadal category is just a formal notation, right? It doesn't have any meaning. It's just a functor. That's all, right? But what it essentially does is, it encapsulates the idea of tensor products. Not encaps. I shouldn't say it encapsulates, but how should I put this? The primary motivation came from algebra only. So basically the idea is, so whenever let's say you look at the category of abelian groups, so people needed, why was the tensor product, the usual algebraic tensor product, why was it, or what does it do? It essentially sort of captures bilinear maps, right? That is what it does. But if you look at it carefully, the category of if you look at all abelian groups and look at bilinear maps, they don't form a category. So what one needs is a category, which is why one passes to the tensor product, and since maps out of A tensor B to some group C is the same as a bilinear map A cross B to C. So what you essentially have done is capture that category like object into a real category, which is obtained by taking tensor products over Z. So the notion of a monadal category, I mean, was meant to be an abstraction of the same thing, abstraction of the category of abelian groups, or more generally the category of R modules, which is why people have used this notation since, I mean, it has been many years since people have used this, but people do use other notations as well, like box. Some people also use circle, dot, etc. But this is just a formal notation. I mean, there is no reason to assume anything extra about this notation tensor. Okay, it's just a formal notation. Yeah, so AB tensor over ZZ. Yes. Yes. No, it's not a monoid object. It's a I mean, a monoid object in the category of categories with Cartesian product will exactly be a strict monadal category. So it's something like a monoid object, but not exactly a monoid object. It's something called a pseudo monoid object. So I mean, since if you look at it carefully, since you don't have strict equalities here, but a monoid object in category should satisfy strict associativity, right? A monoid object in a monadal category satisfies strict associativity, strict unitality. So it's not exactly a monoid object. A monoid object in the category of categories with Cartesian product would, I mean, with product of categories as the monadal structure, would exactly be a strict monadal category. Any other questions? Okay. So AB tensor over ZZ set cross this, and there are other examples. Top with cross singleton. So usually what people do is suppress the notation, I mean suppress alpha, lambda and rho. It's understood they are there, but people don't usually write it. And what else? Can you give me one more example which is different from all this? Yeah, any co-Cartesian, I mean any category with finite coproducts is again a monadal category. It's called a co-Cartesian monadal category. So in particular set this, what would be the unit object here? Yeah, by the way, it's not called phi, it's called oi, because it's a Danish letter. Yes, yes. It's not the Greek letter phi. So these are all different examples of monadal categories. Yeah. And then what else did you see? You saw the notion of a strict monadal functor. Right? Am I right? It was taught, right? Okay. So what is a monadal functor? Can you summarize quickly? So suppose C is a monadal category, and suppose D is another monadal category. We'll write the products in the same, using the same notation. So a monadal functor is first of all a functor F from C to D, and what else? It will preserve the tensor product. Okay. Yeah. And what else? Yeah. So this is called a strict monadal functor because it strictly preserves this. Was anything else taught? Okay. 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 Then you saw the notion of a symmetric monadal category, which is a monadal category equipped with an additional structure. So what is that? So it's a monadal category equipped with yeah, yeah. So this is very important, and this should be kept in mind, that this natural isomorphism, that which we are calling to be the symmetric braiding or the symmetry, is to be thought of as a structure on the category, just like alpha, lambda and rho are thought of as structure. So for instance, it could happen that I could take some other natural isomorphism alpha prime, that by definition would change our monadal category. So these are structures, not properties. Not just, I mean, just saying that two things are isomorphic or two functors are isomorphic is not, doesn't give you the entire data. Alpha, lambda, rho are to be thought of as structures. They are very important. So that is why I should write equipped with a choice of natural isomorphism gamma, choice of a natural isomorphism gamma from gamma with components gamma x y from x tensor y to y tensor z. I mean, sorry, x, subject to certain axioms. And again, the notion of a symmetry is sometimes can be a bit strict, and there are indeed examples of categories which monadal categories which I mean, which have a braiding which is not symmetric. Try to think of one, but that is why one can also relax this slightly. So I'll just write it as a note, can relax this by taking braided monadal categories. So what is a braiding, by the way, on a monadal category? It is again a choice of a natural isomorphism gamma with components as written here, except that for symmetry you need one extra condition, which is that gamma should be in a certain, roughly speaking, self-invertible. So gamma is a natural isomorphism. So gamma xy is an isomorphism. It has an inverse, and its inverse should be gamma yx. This is what a symmetry on a monadal category is exactly. For a braiding, you don't need this condition. You just need that it is a natural isomorphism subject to certain axioms, commutativity of certain diagrams. So I'll just write that can relax this by taking braided monadal categories. So if the definition of a braided monadal category is clear, I would urge all of you to think about an example of a monadal category on which there is a braiding which is not symmetric. Okay, we also saw the notion of a closed monadal category. So what is a closed monadal category? Yeah. 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 So a closed monadal category. So a closed monadal category is a monadal category for which dash tensored with any x from C to C, where C is our category, has a right adjoint. which is usually written as from C to C. And this functor is, as was mentioned, is called the internal Hom. So x comma y will be called the internal Hom from x to y. So it exactly behaves in the same way as a Hom functor should do. That is why it's called an internal Hom, except now that observe that instead of set here you just have C. So in a sense, Homing doesn't take you out of your category, you still stay inside the category. That is why it's called an internal Hom. So give me an example of a closed monadal category. Okay. Set with Cartesian structure. And what else? One more. Okay. The exponentials serve as your right adjoint. Yeah. And what else? I mean, sorry. I mean, the implications serve as your right adjoint, which are given by the exponentials. Yeah. And what else? One more. Okay, that is again of the same nature as this one. How about the category of R modules? Or let's say, let's keep it simple, AB tensored with Z. This is also a closed monadal category. So a right adjoint for this functor is Hom Z A comma gap. Observe that Hom Z A comma B, that is all group abelian group homomorphisms from A to B itself has the structure of an abelian group. Okay. I think you briefly touched on what the definition of an enriched category is, but I don't know if that is examinable. So I'll just mention enriched category, which deals with the Homs of a category. So it usually happens, or in most cases it happens, that in many categories, so it turns out, so usually for a arbitrary category, what happens is that the Hom sets are just sets, or rather classes. But in many categories, the Hom sets have additional structure. For example, one can look at the category of, let's say, vector spaces over something, over a field. Then each Hom set has a structure of an abelian group. It is in fact a vector space, but let's just focus on that. It has a structure of an abelian group. Yes. I mean, which are enriched over k vector spaces. So the point is, yeah. It's an abelian group, but I am not sure if it can be made into an R module in general. Wait, let me think. It can be, right? Yeah, it can be. It will be. So suppose you take f A to B, where A and B are R modules. You define R times F to be this map, sending any A to R dot Fa. This will be an R module structure, I'm pretty sure. Yeah, so for example, one can also look at the category of chain complexes. It turns out that for those who don't know what chain complexes are, you can ignore this comment, but it turns out that the category of chain complexes with chain maps, each Hom set again has a structure of an abelian group, etc. So that is why what happens for enriched categories is that I mean, in addition to making an abstraction of objects of the category, which happens for every category, an object in a category is just a primitive notion, is an abstract notion. What you also do is make an abstraction of the idea of Hom sets and replace Hom sets by Hom objects in some base category. And to make it into a category, what you would need is you would need a composition. So suppose CAB is an object in some category, CBC is an object in some category. What you would want is a way to combine these two and have an arrow from this to whatever this combined thing is to CA comma C. So this suggests that having just a, the base category should not be just a category. It should have more structure, right? Something which can combine objects. And it turns out we have already seen what that is. We have seen a structure of that spirit. So what one can do is consider a monoidal category. So what one does is usually enrich in a monoidal category, or sometimes people also say enrich over a monoidal category. And you have it has an enriched category which is enriched in a monoidal category V, let's say, consists of a class of objects. For every ordered pair of objects, you have a Hom object, which is an object of your base monoidal category. For every triple of objects, you have a composition law, and for every object A, you have an arrow 1 to CA, which essentially is supposed to pick the identity. Note that this is just an abstract object in a category V. This doesn't have any specific attributes or does not have any internal structure, just an object. But it's useful to think of, at least for sets, we know that maps from singleton to an object or a set picks out elements of that set. So in the same spirit, what you want is a map from the unit object to CAA. And we think of this as an identity element for A. Intuitively, what we think is, it's something like a generalized element of the object CA. There is no notion of element, but we can define a map from 1 to CA to be a generalized element of CAA. The motivation comes from sets. Yeah, and this data is again subject to associativity and identity axioms, making it into an enriched category. So I'll not write the definition, I'll just mention the word enriched category. Can you give me some examples? Yeah. Okay. Okay. What else? You mean the category of all posets? What else? Some other examples? Okay. That's already covered because R can be replaced by Z. Something of a different nature. Yeah. Lauvier metric spaces. So Bill Lauvier was this fantastic personality and fantastic category theorist, mathematician, etc. And it turned out that he went to McLean at some point of time and before category theory even came into the picture, and said that I have figured out a way of doing set theory but without using elements. And MacLean sort of dismissed that idea at that point because he felt that it might not make much sense. But then category theory came into the picture. I mean, MacLean and Eilenberg did publish this first paper called The General Theory of Natural Equivalences, which is like the starting point of category theory. But it was actually Lavoisier who came up with this idea of doing set theory without using elements, without accessing internal data, just using maps. So Lavoisier metric spaces are enriched over. I am sure he has mentioned this example in detail. So I'll just write the example. Right. Or rather, let's write it like this. Yeah, so interesting thing is there are a number of things that can be done from here, from this point is, for instance, one can, there is something called magnitude homology, which, and there are other things as well, but magnitude homology is a homology, a theory of homology which studies, so if one looks at usual homology in topology, usual homology, the purpose of usual homology or topological homology is to detect the presence of holes. What magnitude homology does is it can capture the size of holes, etc., etc. So magnitude homology is a theory applicable for enriched categories, but since according to Lavoisier, metric spaces are also enriched categories, so that entire theory could be applied to metric spaces in particular. And in metric spaces, one can talk about sizes, and hence magnitude homology is applicable to metric spaces, captures sizes of holes. So magnitude homology is like a geometric theory, in contrast to topological homology, which is a topological theory. And there are other many other uses of this as well. I mean, one can talk about capturing concepts from analysis using category theory, etc., etc. And it turns out that many people have done a plethora of work on this. But yeah, it's I mean, discarding everything else, it's beautiful in its own right. This example is absolutely beautiful in its own right. Yeah, any other examples? Okay, and what else did you now comes the most interesting and most important thing, which is you also studied the notion of abelian categories. So abelian categories are, in fact, let's start from the beginning, pre-additive categories. So you studied pre-additive categories. So what is a pre-additive category? Okay. In short, what can you say in short? I mean, based on what we, yeah. So, category enriched over the category of abelian groups. So in other words, what if you break down the entire thing, what you would have in detail is that a pre-additive category consists of a class of objects. For every ordered pair of objects, there is an abelian group, which we'll call the Hom abelian group, let's say, from the first object to the second object. For every triple of objects, what you would have is a map from A, B tensored over Z with a comma c, b comma c to a comma c. So again, since tensoring over Z is has a universal property, we can think of it as a bilinear map from this cross this to this. So why are we actually coming to this thing, coming to cross? Essentially because what we want is we want to think of a preadditive category also as a category. So it has all the data of a category, but in addition what we have is, first of all, each Hom set is not just a set, it's an abelian group. Secondly, composition should be bilinear in both variables. So that is what the idea is, or the definition is, of a preadditive category. So we can also write equivalently it's a category. Equivalently, it's a category what? It's a category with whose Hom sets are abelian groups and composition is bilinear. Then comes the notion of an additive category. What is it? Preadditive category with products and a zero object. Okay. And yeah, yeah. So the idea is, so why is it called a ringoid? So what you are essentially doing is, first of all, so let's look at groupoids first, or the idea of groupoids. What do groupoids do? A groupoid with one object is exactly a group. So what you are doing is you are thinking of an algebraic structure, or rather the elements of some algebraic structure, as arrows in a single object category, and then studying the many object versions of that. And hence, instead of groups, what you are considering is a groupoid, which is a category in which all arrows are isomorphisms. For a ring, you can also think of a ring as a category with a single object. It is exactly a preadditive category with a single object. And how do you get to ringoids or preadditive categories? Just study the many object versions of that. So you study a category with many objects which has the same kinds of properties, namely each Hom has an abelian group structure, composition is bilinear, which is exactly the notion of a preadditive category, which is also referred to as a ringoid. So I'm sure he has mentioned how modules over a ring can be thought of as additive functors, right? So similarly, so left modules form this functor category from R to AB, and right modules are this functor category R up to AB. So one can just, use this idea to define modules over rings with several objects, right? Just take a preadditive category R, then look at all additive functors from R to AB. Or look at our additive functors from R up to AB. It turns out, and in fact, it turns out that so this concept was first formalized by I guess Mitchell, P. Mitchell, and it is applicable in a ton of different contexts, in a number of different contexts. Like, for example, in representation theory, what else? Yeah, in representation theory, in the I'm sorry, I can't remember the name of the paper right now. Yeah, but my point is that whatever commutative algebra you do with commutative rings, essentially most of it can be reproduced in this several object setup as well. So for instance, one can talk about tensor products, one can talk about uh, so tensor product of you, usually people can talk about the tensor product of a left module over a ring and a right module over a ring, and the tensor product is an abelian group. Here also one can talk about the tensor product of a left R module where R is a general priative category and a right R module, and one can and that is again an abelian group itself, AB, an object in AB, etc., etc. One can do a lot of different things, and in fact the significance of all these things might become clearer in the next week when I guess he will talk about Grothendieck categories, right? That's that idea topic of the, yeah. So Grothendieck categories are really, I mean, so these are like the gateways to doing commutative algebra but over general categories. Okay, I mean gateways to commutative algebra, categorical algebra, I should say. So yeah, this is really powerful and really important. Yeah, and then comes the very interesting notion of an abelian category. What is an abelian category? Category with equalizers and co-equalizers. So let's just write it in this way: additive category with kernels and co-kernels. So what is a kernel, by the way? Yeah, 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 yeah. And dually, if you take the co-equalizer, you get the co-kernel. Yeah. So is this just all the axioms that is present for an abelian category, or is there something more? Okay. And what do you mean by that? What do you mean by that? Yeah. And in addition, and what the dual thing, right? That each co-kernel should be, I mean, each epimorphism should be a co-kernel of some map, or equivalently a co-equalizer of some parallel pair, or equivalently a regular epimorphism. Okay. And in fact, from this data, you can also show this, that for an abelian category, if you assume that every monomorphism is a kernel of some morphism, that is, if every monomorphism is regular, you can show that every monomorphism is in fact the kernel of its own co-kernel, and every epimorphism is the co-kernel of its own kernel. Okay, kernels, co-kernels, and every, and with the property that uh, monomorphisms are regular. Monos and epis are regular. Sometimes also called normal. Yeah. Anything else? Okay. So this, as I make, sorry. No, certainly not. Why would you even think like that? For instance, I mean, we have seen many examples in our BSc training or MSc maybe. We have seen many examples of sub-modules of a module which are not direct summands, right? So that's the same thing. So I mean, it's not true. In general, it's not true. Certainly not true. But for vector spaces, this is true. Because the category of vector spaces is something called a spectral category, in the sense that every object is both injective as well as projective, etc., etc. So you have all these nice properties that every sub-object is a direct summand, etc., etc. Or in other words, all exact sequences split, etc., etc. Yeah. Any questions so far from the content? I have a question. I'll ask later. But yeah, any questions so far? Okay. So my question is, I don't know what quantaloids are, but from the name I can guess that it should be a many object version of a quantal. So a quantal can be thought of as a category with a single object, and a quantaloid should be a many object version of that. So my question is, how is it exactly enriched over soup lattices? Yeah, I mean, yeah. Okay. Okay. Let me not write it. Yeah. If you take any complete lattice, by which you mean a partially ordered set, which is a lattice such that it has all soups and infs. Yeah. Okay. 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 Hmm. Okay. So it distributes over joints, arbitrary joints. Okay. So this is what a quantal is. Yeah. Yeah. Okay. One second. One second. Since it distributes, it also has a right adjoint. And then what? Oh, okay. So what you are saying is, so you take a soup lattice, right? X, let's say, and what you are doing is you are defining an operation on X, which is your star. So star is from X cross X to X. Yeah, so you are thinking of X as a category and star is a monoidal structure on X. Then? Okay. 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 So why are you talking about this having a right adjoint? Okay, and why does this? Okay, and just for the viewers, why does this have a right adjoint? If it distributes over joints? Yes, exactly. Okay. Yeah. Since the joins are limits. No, sorry. Since the joins are co-limits. 1 second. 1 second. Join comes down. So there is a map from everything to the join. Yeah, but then how would the general adjoint functor theorem apply here? Oh, sorry. I'm sorry. I'm completely. Yeah, you are right. Yeah, rather the dual of the general adjoint functor theorem. So is the solution set condition also satisfied? Okay, we can think about that later. But I assume it is satisfied. Yeah, so this is what a soup lattice is, and then okay. Okay. Yeah, it should be that only. I mean, categories enriched over soup lattices should be quantaloids. Yeah. Just as categories enriched over AB are ringoids. Okay. Similarly, one can also talk about algebroids, etc., etc., which are categories enriched over vector spaces, etc. And then one can talk about co-algebroids, etc. Okay, we can discuss that later, but they are famous. They are really. I mean, apparently they are pretty famous. Okay, so let's quickly jump to the problems. Yeah, so this is our first problem. So let's see tensor I be a monoidal category. Show that these two functors are equivalences of categories. How would we do this? Tensoring with I from C to C is an equivalence of categories, as well as I tensored with something from C to C is an equivalence of categories. How do you show this? Yeah. Okay. Okay. Oh, wait, 1 second. It's row, yeah. So from this to A, you have an isomorphism for every A. Yeah. So what does this imply? Yeah, you have lambda. You can take lambda. Yeah. Yeah. Sorry, I didn't get your point. What exactly are you, which definition of equivalence of categories are you using? It has a quasi inverse. Okay. Okay. Fine. whatever definition you are using is okay, but tell me which definition are you using? Hmm. No, I understand, but we need to be very precise about this. So how? So let's focus on one functor only. Bar tensor with I from C to C. We want to show that this is an equivalence of categories. How do we show it? Just tell me. Yeah, that's okay. But I mean, there's no point in going to adjoint equivalences. Because for adjoint, what are adjoint equivalences? They are adjunctions in which the unit and co-unit are natural isomorphisms, right? Yeah, so why would you? Okay. Yeah. Okay. See, the interesting thing. Okay, continue. Continue, continue. So from FGA, I tensored A. Yeah. Yes, and one can use lambda and rho separately. So this is lambda A first, tensored with one I, which is A tensored with I, and from there you use rho A to get to A. Yeah, yeah. So FGA is isomorphic to A. Why is it naturally isomorphic? Why does this give you a natural isomorphism from FG to identity? Yeah. Yeah. Okay. So very loosely speaking, or in fact, this is the exact reason is that rho and lambda themselves natural isomorphisms. Yeah. So from FGA to A, you have, so therefore what we have is a natural isomorphism from FG to I, and what we can also show, I mean, sorry, identity on C. And what we can also show is we have a natural isomorphism from 1C to, let's say, GF, right? And that is enough to claim that this is an equivalence of categories. But my point is that, is there a need to really consider bring G into the picture? I mean, one thing that this does is actually show that both F and G are equivalences of categories. But can we not, I mean, you could also just consider F and choose another quasi-inverse for F. For example, let's say the identity functor itself will be a quasi-inverse for F as well, right? This is clear, right? So the point is that A tensored with I to A, you just take rho A. This is by definition a natural isomorphism, and this is actually saying that I mean, F composed with identity on C is naturally isomorphic to F, and identity on C composed with F is naturally isomorphic to F at the same time, right? Okay. So just to write a complete argument, let's just use your idea and let's just quickly finish this. So yeah, so observe that for each A in C, FGA, which is by definition I tensored A, tensored I. From this you can go to A tensored I using lambda A tensored 1I. From this to A you can use rho A. So you have this isomorphism for every A. Check that this gives you a natural isomorphism. So morphism from FG to identity on C, and also check that let's say GFA, which is by definition A tensored I, tensored A, I mean tensored I, sorry, to I tensored A. What is this? This is 1I tensored with rho A to A, which is lambda A, constitute, so where A is in C, constitute a natural isomorphism from GF to identity on C. Yeah. So F and G are equivalences of categories. And what I was saying is that observe that rho itself is a natural isomorphism from this functor gap tensored with I to identity, right? So any functor which is naturally isomorphic to identity has to be an equivalence of categories. Any functor which is naturally isomorphic to identity, I mean for G also, has to be an equivalence of categories. But I like this solution more because it uses both F and G and simultaneously does the job instead of doing it separately. Okay, so any questions? Okay. Okay, state whether true or false. Yeah. So, what is the time? 7:04. Okay. So, yeah. We need to state whether the following. Yeah. Yes. So state whether the following statements are true or false with appropriate justification. Firstly, if A is a set, then set over A has a Cartesian monoidal structure. Is this true or is this false? Yeah, the slice category. I mean, yeah. So any object is an object X, that is a set X together with a map X to A, which can be thought of as a bundle over A. So is set over A does, okay, okay, why? Yeah, rather the other way, that is the Cartesian product, I mean the categorical product, the product in this category set over A, in the slice category set over A, are exactly pullbacks in the category A. So I'll just mention this. Since set has pullbacks and products in set over A are exactly pullbacks. I mean, one intuitive reason. So one intuitive reason is this, that so the category set has pullbacks, and this is true in general, that suppose you have a diagram like this, a co-span diagram like this, and suppose the pullback of this diagram exists, let's say P, and suppose in addition what you have is this common object turns out to be terminal, then this pullback P is exactly the product of these two objects. So what happens in the case of set over A is, suppose you take I mean in set over A, the terminal object is the identity arrow A to A, and any pullback in the category of sets where A is the common thing, so X to A, Y to A, suppose P is your pullback, which we write as X crossed over A with Y. Suppose this is your pullback. You can interpret this entirely as a diagram in set over A. Observe that X is a set over A, Y is a set over A, as well as X cross A with Y is again a set over A, and A itself is a set over A. So you can think of this as a diagram, A comma 1A. Let's suppose this arrow is F, this is G. So Y comma G to this, X comma F to this. And this has a, common structure here. Interesting thing is that this is the terminal object here, and hence this has to be the product. So I'll just write this short comment, is that for any pullback square in a category, for any pullback square in a category, let's say this is A. If A is terminal, then P is a product in the category. And A to A, 1A is the terminal object. In set over A. So this is the reason that products in set over A are exactly pullbacks in set. And since set has pullbacks, so set over A has products, and any category with finite products is it has binary products and it has a terminal object. So it has all finite products. So set over A is set over A has finite products and a terminal object. So set over A is a Cartesian monadal category. I mean, it's enough to just say, it's just enough to say that it has finite products. So set over A has finite products. So set over A is Cartesian closed. I mean, sorry. So set over A is a Cartesian monadal category. Yeah. So this is true. So statement 1 is true. What about statement 2? Top with Cartesian product is Cartesian closed. Yeah. 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 They might not have, depends on the domain and the codomain, but it could happen that it's not exact. I mean, it's supposed to be the internal home of A from X to Y. It's supposed to be a topological space. It could happen that it's not the set of continuous maps, something else. That can happen, right? Some subset of the class of all maps, etc., etc. So I'll just give you a hint on this, and you can come up with an you can complete it. So what does your intuition say? What does your intuition say? False. So the way to see this is show that bar cross Q, the topological space of rational numbers from top to top. So if top with Cartesian product were Cartesian closed, if it were a closed monadal category, then this functor should have a right adjoint, right? Which means that this functor should be a left adjoint, which means that this functor should preserve co-limits. So this is how one can show in general that some functor fails to be a left adjoint or some functor fails to be a right adjoint by showing that that functor doesn't preserve some kind of co-limit or doesn't preserve some particular limit, etc. So what you need to show that this functor doesn't preserve co-limits. In fact, what you can show that this functor doesn't preserve co-equalizers. So in other words, what I'm suggesting is you can come up with a parallel pair of maps with some particular parallel pair of maps such that the co-equalizer of that parallel pair is not preserved by this functor. Okay. So this is a hint. Okay. So next question. Any questions, by the way? Okay, so next question, if A is an additive category, then for any object A in A, the functor co-represented by A from A to AB. Of course, we know that if A is an additive category, each Hom set is actually an abelian group. So this functor actually lands into AB. what we want to show is that this functor preserves finite coproducts or disprove. So is this true or false? What do you think? Okay. It should preserve finite coproducts. Is that what you are suggesting? Okay, why? Okay, right. Yeah. Yes, this is rather the intuition. So, yeah. Okay. Yeah. Yeah. So the idea is basically this, that, for example, in the category, you are right. In the category of abelian groups, if you take a finite direct sum, you also have projection maps to each individual summand, right? So usually what happens for what is the idea of coproducts? Coproducts are co-limits, that is, they are characterized by maps going out of them, and coproducts themselves, just as all co-limits are canonically equipped with some structure maps, which are the co-projection maps, right? Going from uh, some object x to the some object xi to the coproduct xi. You have maps like this, right? Let's say some object x0. Now this is in general true for any category, and similarly you have the dual structure maps for products. What happens in the case of in the case of AB, let's say abelian groups, is that for finite coproducts you also have something called projection maps, right? So A1 direct sum up to AN, you have a projection map to each AJ, right? So if you take a map from A to this, you can compose it with AJ, and what you have is a map from A to AJ, which essentially says that maps from A to coproduct are to the finite coproduct are exactly uh, given by a tuple of maps from A to each direct summand. Right. Conversely, if you have a map from A to AJ for every J, you can cook up or build a map from A to the direct sum. So what is the generic idea, or what is the generic thing that we are pursuing here? I think that was mentioned this week. What is that word? So it's the, yeah, there was some specific word that was mentioned this week in the lectures, I'm pretty sure, which is the notion of a byproduct, right? So the point is that just with these minimal assumptions, and that is why these things are so interesting, just with these minimal assumptions, that if you just take an additive category, which is by definition supposed to be just a pre-additive category with products and a zero object, what you can actually show is that finite products are exactly the same as finite coproducts. So if you take a finite product, you can actually show that that finite product has the structure or has the universal property of a coproduct. So for instance, suppose you take a binary product x cross y. Okay, what I would want is to think of this as x coproduct y as well. So what I would expect is to have a map from x to this. How do you think can we get a map from x to x cross y, which is to be thought of as a co-projection map associated to the co-limit? How can we obtain a map from x to x cross y? Yeah, exactly. Because you have some special map which is the zero map from x to y. So what you can do is you can take this map from x to y and you can take identity map from x to x. Now by the universal property of what does do you get a map from x to x cross y? No, from the universal property of products, right? Because we don't yet know whether this is a coproduct. Yeah. So from x to x cross y you have a map, from y to x cross y you have a map, and you can show that this maps together with the canonical structure maps, that is the projections that you have, satisfies those 4 or 5, I don't exactly remember, those equations for byproducts, those properties for byproducts. So interesting thing is this only, that in an additive category, finite products are the same as finite coproducts. So now can we finish this in one line? So I'll just mention that in an additive category, finite coproducts are the same as finite products, isomorphic to finite products of the same objects, which are the same as finite byproducts, or rather byproducts. And that is why one usually denotes byproducts by direct sums, just to mimic what happens for abelian groups or harmonics. Yeah, now can we finish this problem in one line? Oh, okay. Yeah, continue. Okay. Okay. Yeah. That's understood. I mean, you are just mimicking the same idea as for abelian groups. But can we just have one line, finish this in one line? Do we know anything special about the Helm functor? In general? It preserves limits, right? Try to think of it in this way. Yeah, so no, since finite coproducts are the same as products here, and this functor preserves products, so it will preserve coproducts. So the result, and Helm functor always preserves limits. Keep this in mind, not co-limits. Helm functor is supposed to be like a right adjoint, supposed to behave like a right adjoint, right? Yeah, the results. Oh, sorry. The result is clear. The result is clear from the fact that the Helm functor preserves limits. So if you take a coproduct in A, this, you think of it as a product, this functor will map it to a product, of course. Now AB is again an additive category, so finite products are the same as finite coproducts, and you are done. So 3 is true. And what about 4? Every abelian category is complete and co-complete. Is this true or false? Okay. Okay. You have to be a bit careful here. What is the definition of an abelian category? It's an additive category which has equalizers, co-equalizers. Every monomorphism is a kernel. Every epimorphism is a co-kernel, right? But what is an additive category? If you look at its definition, what is an additive category? Pre-additive category with, okay, so yeah, I should have observed this earlier, with binary products and a zero object. Yeah, so what does that mean? Yeah. So what do you think? What can we say for sure that this is true for any abelian category? What can we say surely? Okay. That is, it has all finite limits and it has all finite co-limits. Because it has binary products, or rather finite products and equalizers. But is it necessarily also complete? So this might be again a very specific example for the readers, I mean the viewers. Uses some amount of commutative algebra, but the idea is, if you know what a Noetherian ring is, okay, forget Noetherian. Okay, yeah, no need to even consider Noetherian. Just a minute. Take the, oops, take the category of finitely generated abelian groups. This is again an abelian category. Why? Why is this an abelian category? So first of all, this has a zero object, we can agree. This has finite products, finite co-products. What else can we say? Does it have kernels? In other words, if suppose A and B are finitely generated abelian groups and F is a map of finitely generated abelian groups from A to B, is the kernel also finitely generated as an abelian group? Why? Yeah. And why? One line. Because Z is Noetherian, right? And similarly, you can show that co-kernels, which are quotients, they are finite. That is always true. I mean, if some group is, if some object is finitely generated in a, let's say in an abelian category, if some object, okay, in a Grothendieck category actually, if some object is finitely generated, then any quotient of it is again finitely generated. This is always true. Yeah, so it has kernels and co-kernels. Every map is a kernel of some morphism. Every, in fact, is a kernel of its own co-kernel, and every, I mean, every monomorphism is regular and every epimorphism is regular. Yeah, so it's an abelian category, but it doesn't have infinite products. Nor does it have infinite co-products. Okay, that is very easy to see actually. So for example, you can take Z. Z is finitely generated, but coproduct of n many natural number many copies of Z is not finitely generated. Picard group. What? Oh, I see. Okay. Okay, 1 second. This is not co-complete. Not complete. I mean, neither complete nor co-complete. By the way, what is the definition of a complete category again? Just to make sure that we know we are on the same page. Sorry, one more time. Yes, and it has co-limits of it has limits of any shape and it has co-limits of any shape. When you say size, that doesn't really. Size again has a special meaning in category theory. Right. So this is neither complete nor co-complete. Because for instance, Z is not finitely generated. Z is finitely generated. Yeah, this is abelian. I should also write this. This is an abelian category. This is neither complete nor co-complete. For example, Z is finitely generated, but Z direct sum dot 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 n copies. Okay, I should write the copies. Yeah. So on is not finitely generated. What did you call this group? Yeah, this is the coproduct in the category of abelian groups, right? Yeah. Specker group. Let's write this name. SP SPCKER. Okay. Yeah, that is what I was thinking. Specker group. Okay. Okay, so that finishes. Yeah, so what happened to this? This is false, therefore. So 4 is false. Okay, let's move on quickly. Any questions, by the way? Okay. So suppose that C tends. Two more questions. Yeah, suppose that C tensor die is a monadal category. Show that this functor from C cross C to C, what it does is takes xy in this order and maps it to the flipped tensor product y tensor x. Show that this is also a monadal structure on C. So we will just quickly mention hints only, and so to clarify, to show that this is a monadal structure, first observe that tensor tilde from C cross C to C is a functor. Why is this a functor? Easy to check actually. More general, precisely saying, this is actually this composition. So from C cross C, this product category to C cross C, you have this twist map which sends x comma y to y comma x. It's not right to call it twist. Let's call it twist, no problem. I should say flip, but okay, yeah. And from C cross C to C you have tensor, which sends y comma x to y tensored x. So this is a functor. Composition of two functors is a functor. Okay. What else do we need? We need a unit object. What do you think should be the unit object for this monadal structure? I. Okay. Take I to be the unit object. This needs to be verified. Some calling an object to be a unit object is not all. We need to check that it is actually the unit object. So take I to be the unit object. We'll clarify this. What do we need next? An associator, an associativity constraint, an associativity coherence isomorphism. So do we have one? At each component we can compose with twist map. What does that mean? Okay, so let's write it properly. So take alpha tilde to be the natural isomorphism with components x tensor tilde y tensor tilde z, which we know is z tensored with y tensored with x. What do we do now? Or rather alpha inverse zyx in the convention that we are following. Yeah, it's okay. Yeah. And does this do the job? Precisely because this is exactly equal to x tilde, I'm sorry, x tensor tilde y tensor tilde z. Right. Okay, this is indeed natural because alpha is natural and hence alpha inverse is natural. So x, y, z. Yeah, what should we take rho to be? Rather rho tilde from, okay, let's write it. Take rho tilde to be the natural isomorphism with components. X tensor tilde I, provided we use this for notation for rho, just trying to be consistent. Yeah. X tensor tilde I to which is equal to I tensored x. From this to x we need something. So lambda x to x. Yeah. X in C. Yeah, similarly take lambda tilde equal to rho and check that the pentagon axiom. So this pentagon axiom came from the name, came from Stashev, who was a topologist, actually an operad theorist, and Stashev. Yeah, Stashev. So so there are things called A infinity algebras, and or rather E1 algebras, which are given by operads. And I mean, the pentagon axiom was an attempt to weaken associativity in a certain way, which I can't really say right now very precisely. That would involve some work, but yeah, that was the idea for. I mean, there is an analogous thing called the pentagon axiom in, let's say, algebraic topology, and this name comes from there. So check that the pentagon axiom and triangle axiom hold. Okay. So this makes, don't want to use any more pages. So this makes C tensor tilde I into a monoidal category again. Okay. Quickly, let's move on. This is easy. Yeah, any questions? Okay, so what do you think? So what is the definition? What is the idea of a skeletal category? A category that is a definition of skeleton. So what a skeletal category is that any two isomorphic objects are equal. Okay. So if X is isomorphic to Y, then X has to be equal to Y. Roughly speaking, it has no flesh or irrelevant data. That is what it is. And what is the skeleton of a category? It is just a full subcategory, or rather the full subcategory obtained by choosing exactly one object from each isomorphism classes of objects. Each isomorphism class of objects. So what is a skeletally small category? No. Skeletally small or essentially small. What do you think this means? What other meaning can come out of this? Skeletally small means it has a small skeleton. That's all. So oftentimes it happens that we want to show existence of limits, certain limits or certain co-limits in categories, and as we all know by now that limits and co-limits are usually taken for diagrams whose domain category are small categories, and it many times it happens that the domain categories of the diagrams or the functor whose limit or co-limit we are considering is not small. So what one would then hope is that the domain category should be skeletally small, so that instead of considering all objects, one can just focus on one object from each isomorphism class of objects, which now forms a set. Okay. Is this okay? So a skeletally small category is a category which has a small skeleton, or which is equivalent to a small category. Any category is equivalent to a skeleton of it. So yeah. So give an example of a skeletally small abelian category. What do you think? Why? So first of all, can you give me an example of a skeletally small category which is not small? Can you give an example of a skeletally small category which is not small? Okay, so is the category of let's say finite sets, what do you think? Is that skeletally small? Why? Yeah, yeah, yeah. So the set of isomorphism classes of objects, I mean, you have a bijection from that set to the set of natural numbers, right? I mean, you have a bijection from the class of all isomorphism class of objects to the set of natural numbers, which therefore means that the the class of isomorphism classes is actually a set. So this is a skeletally small category. Now we sort of want to algebraify, if that's a word, this example. So what is this? I mean, we have seen this previously, for example, in our BSc training, etc. So, I mean, there is a way to reduce. So, what does this cardinality thing do? It reduces some mathematical object to a number. For instance, it reduces a finite set to a number, right? So, do we have an algebraic example of the same sort, which reduces some algebraic object to a number? Something similar to cardinality. Take the category of finite dimensional vector spaces, let's say. What do you think? We know that any vector space V which is finite dimensional has to be isomorphic to some Fn, right? That does the job. By the way, just out of again for the viewers, so we know that for every vector space V, there is an isomorphism from V to some Fn for some n. My question is the, I mean, can we have a natural isomorphism? I mean, this again doesn't really make that much sense. Uh, yeah, this doesn't make much sense because yeah, you want to say something? Okay. Yeah, this doesn't make, yeah, yeah. No, no. So, I mean, this question doesn't really make sense because a natural isomorphism should be between two functors, right? So, I mean, the right hand side is not a functor of V at least. So, okay. Okay, we'll come to this. Okay, so give an example of a skeletally small abelian category. Take the category of finite dimensional vector spaces. Vector spaces. The class of isomorphism classes. This is an abelian category. So the class of all isomorphism classes of objects or that is vector spaces is okay, is in bijective correspondence. There is a bijection. With the set n of natural numbers. So the class of isomorphism classes of objects is a set. So this is skeletally small. And why is this abelian, by the way? Again, because of the same reason why AB was abelian. And in fact, this is easier to prove here. If you take, sorry, yeah, for any field K, and for any field K, you mean K is a field, right? Yeah, for any field K, K mod is abelian. But this is not true for any ring, of course. Oh, sorry, I'm sorry. Oh, what I mean to say is finite dimensional K modules are abelian for any field K. Yeah. In general, for any ring R mod is abelian, but finitely generated R modules need not be abelian unless R has some nice properties. Okay, so the class of isomorphism, class of objects is a set. Yeah. Okay, so my question was sort of irrelevant because I mean you understood, right, why it doesn't make any much sense. Because you need to have a functor in the same argument on both sides. You need to have functors in the same argument on both sides. Yeah. Since we were on that topic, can you give me an example of, so what is a natural transformation? A natural transformation is a class of arrows which is in a certain way compatible with composition, right, in a certain specific sense. So can you give me an example of a class of morphisms? Okay, so can you give me an example of a functor f, a functor g, and a class of morphisms fa to ga, for one for each object A in their, so f and g are parallel functors, so assume f and g are both from A to B, but which is not natural. I mean, there's a reason I'm asking this, I'll tell you next. But can you think of a class of arrows or give me an example of one which is not natural? Okay. F is identity. Okay. Yes, so we just want an example. We can just replace A by set also. Set, so one set. In fact, I would rather take G to be one identity on set and F to be some functor, and A is a set in set. Yeah. So the reason I am asking this is what exactly is the purpose of having a natural transformation, or what exactly does the naturality axiom say or mean, roughly speaking? What is the intuition behind it? I mean, why would all of a sudden we want that a class of arrows satisfy this property that for every arbitrary arrow in the domain category, you should have a commutative diagram like that? What exactly does it capture? Or does it, why, I mean, what is so natural about it that we are calling it a natural transformation? Yeah, so loosely speaking or roughly speaking, it, I mean, I mean, rather, what, I mean, a better way would be to say that it's defined in the same way across all objects, right? Yeah, I mean, yeah, so it really doesn't depend on the object A. It's defined in the same way, in whatever way it is defined for A, it is defined in the same way for A prime as well. So a very common example is of a natural transformation motivating this is, can you give me one example? Yeah, which sort of captures this idea. Okay. Okay. Hmm. So what you are saying is you are taking GRP, you are taking GRP to GRP, you are taking identity on GRP, and GRP to GRP, you are taking the functor OP, sending G to G up. Okay. So when you say G up, you are thinking of G as a category. Oh, okay. So, oh, so what you are saying is G up is this group. A star B is, I mean, A star prime B is B star A. Okay. I mean, yeah, that's the same thing. Yeah. Okay. So what you are claiming is that there is a natural isomorphism from the first to the second. Okay. Um, is that true? Uh, uh, so G to G op. So what is your isomorphism identity map? Okay. Because you don't have anything else here that you can, anything natural, right? Oh, okay. So what you are doing is, oh, why not? Yeah. You're sending G to G inverse. Okay. And okay, so this won't happen for a monoid. So G star H gets mapped to H inverse star G inverse. Okay. Yeah. It's defined in a natural way. I mean, it's defined in the same way for all G. Yeah. So yeah. So the idea of a natural transformation captures precisely that. There are no arbitrary choices involved in the process. Okay. Good example. Yeah. So whenever there is an arbitrary choice involved, you can say that something is not natural. For instance, you could take f to be, let's say, the constant functor on the singleton delta 1. So what you would have is a map from 1 to GA, where 1 is a singleton set, and you can, for every A in set, you can, let's say, choose a, I mean, this again is subject to certain things, set theoretic issues, but you can choose an element from GA, from the set GA. The idea is that that won't be natural, for example, because you are making arbitrary choices. So something similar actually happens. For instance, why we actually talked about this was V is isomorphic to Fn, finite dimensional vector space is. I mean, I shouldn't really bring that example up. That is not a well posed question. But the idea is that maybe that would make sense subject to certain things. So for example, every finite dimensional vector space is isomorphic to its dual, let's say, right? So this also is not a good example, because the dual functor is supposed to be a functor from vect op to vect, right? And the identity functor is supposed to be a functor from vect to vect. So you can't really talk about a map from one to the other. But my point is that this isomorphism, I mean, very if you think of it intuitively, this isomorphism is no, we, yeah. Okay. No, that I understand, but the point is that this dual functor is a functor from vect op, right? To vect. And identity is a functor from vect to vect. So you can really talk about a natural transformation from identity to this, right? But the idea is that whenever you try to form such an isomorphism, forget for the time being that their domains are distinct. If you try to form an isomorphism from one to the other, you always need to choose a basis, and whenever you make an arbitrary choice, that is no longer natural. Okay, yeah, I think we have come to an end, and we can stop here for today. Any questions? Okay, so I'll stop the recording and see you next week. And just a fair warning to all the viewers. I have been told that many people are using some kind of AI for writing assignment solutions, and which are therefore close to perfect. So this is just a warning that, so I'll just write the warning that oh, I see. But still, I have been told that many people have been using rather taking direct screenshots. Maybe not ChatGPT, some other thing. I see. So yeah, that brings us to the end of week 9. See you next week. I'll stop the recording.